this video every day until the day of the exam. Okay, command terms discuss. You give arguments for and against what is being discussed. It's 4 marks. You're going to give 2 arguments for and 2 arguments against. Evaluate. You give strengths and limit. And if it's 4 marks, you give 2 strengths and 2 limitations. If it's 2, 1 strength, 1 limitation. Interpret. We're going to look at an example. So you describe and explain why the results are what they are and whether they're significant or not, and also what they mean in context of the question. Sketch, you need to bring a pencil and a ruler. Compare and contrast. So compare, you just give the similarities, and contrast, you give the differences. And in biology, you can find compare and contrast where you do both things. Distinguish, just also like contrast the differences and apply using the theory, principle, equation, etc. Before I meant watch this video every day until the day of the exam. Okay. Tool 1. So ethical considerations. It's just going to be everything related to safety. So personal protective equipment, such as in the specimen paper, the helmet with the foam core liner reduces acceleration of the head, and because there's going to be less acceleration, there's going to be less force when hitting something, right? Maybe hitting the ground, reducing the risk of concussion, and this is Newton's second law. So warming up increases muscle temperature, improving muscle elasticity, and reducing injury risk. The gradual increase in intensity reduces risk of sudden application of force, which would be acute trauma, and increased heart rate to muscles improves the oxygen delivery to them. Or also preventing participants from exerting themselves too much, high exertion, so preventing low energy availability that when prolonged leads to red S, preventing abnormal application of force, gastrointestinal discomfort, hyper or hyponatremia related to sodium, preventing dehydration from cardiovascular drift, which is the loss of fluid or sweat from prolonged submaximal exercise in hot conditions, and also taking into account the menstrual cycle, where estrogen causes a glycogen sparing effect and joint stiffness that can lead to joint injury, or the thermogenic effect of progesterone that can disrupt sleep quality. Now, how to measure heart rate and respiration rates. There's also more of this later, but you can look at your radial artery, like put your finger there, use a stethoscope, you need to know this for bio, and respiration is just going to be counting breaths. Video analysis we're going to look at later. Okay, how to test aerobic capacity. There's a 12-minute Cooper run and the multi-stage fitness test, the bleed test. Body composition is going to be BMI and body fat percentage. Testing the reaction, the ruler test we did in class. Agility, the Illinois agility test, and the use of the methods to quantify perceived exertion. Just in case, know that there's the Borg scale or the modified scale, and the use of questionnaires to quantify psychological constructs such as all the psychology topics. For example, the 5 personality traits: openness to experience, conscientiousness, extra introversion, agreeableness, and neuroticism. Discuss the use of ergometer data, so technology, visual data, for assisting a coach in the selection of rowers. So it provides data on rowing performance that you would not be able to see, such as force exerted or drive length. You can identify which rowers have the fastest times, you can have standardized comparisons, and you can monitor the change, the improvements over time. Then, why can the data from the ergometer screen influence intrinsic motivation? Well, it compares the actual performance of the athlete to the ideal performance. So it gives an opportunity to set goals. It can be task oriented or ego oriented, and it allows autonomy, so more self-determination and motivation. The reliability of using photographs to identify the type of shoe. So it can be reliable because there's more time to correctly identify the type of shoe, because you can just look at the photograph a lot of times. And however, you could misidentify it if the angle or the photograph is blurry. So these kind of questions discuss, for example, give a reason why in argument for, an argument against. And this is going to be like logic. Some things are less logical, which we're going to look at, but these questions, yeah. Maths. So appreciate when some effects can be ignored and why this is useful. For example, air resistance in gymnastics is going to be negligible, or in rowing, so you want to take into account into calculations. Um, Calculate, okay, we're going to look at these later. Just have in mind that the standard deviation, you need to know this for maths though, it's going to be, this is in the data booklet, so 60% are within one standard deviation, 95% within two, and 99.7% are three standard deviations from the mean. This you know from maths. And remember, very important, that the coefficient of variation is in the data booklet. So if they ask you to calculate it, quick look, super easy, 100 times standard deviation over the mean. Quick look at the formulas you need to remember. So percentage change is 1 minus the new value over the old value times minus 100. Difference between two values. So these little bars mean that if you get a negative answer, for example minus 5, you change it to the positive. So the answer cannot be negative. It goes for percentage change as well, though this formula always gives the right answer. No, even then, if it's the percentage change is 5%, they will accept minus 5% in uh, sport science, but not in maths. So remember to change it to positive and say 5% decrease in the case of being negative. Percentage difference, it's going to be the difference between the two values divided by uh, the sum of the two values divided by 2. So percentage difference equals value 1 minus value 2 over 0.5 times value 1 plus value 2. Percentage error, we know from maths, remember, again, if it's negative, you change it to positive and say decrease. Percentage uncertainty is going to be the absolute uncertainty over the measured value. For example, if you have 400 plus minus 4, you do 4, use the positive one, not the, even though it's plus minus, use the positive. 4 over 400 times 100 gives you 1% as percentage uncertainty. Now, discrete variables have fixed intervals, for example, number of push-ups, but continuous variables have no fixed intervals. Height, weight, even if the graph shows like height of 10 centimeters, then 11, then 12, and there's like no decimal shown, height will always be continuous. Evaluate the use of a t-test to determine the significance of the results in this table here. So this table shows that it compares the means of the two sets of data, and there is sufficient data. So remember, this is evaluate, reasons for and reasons against. So it can be used because it compares the means, says here, and there's enough data. However, the sample is not necessarily randomized or representative of the entire population. Then you have these, you know, from maths. And if you encounter strange units such as joules or uh, acceleration due to gravity on Earth, just look at the data booklet. In the graphs, if there's error bars in the graphs and they represent uncertainties and not standard deviation or standard error, and they overlap, just like this, it can cover or mask statistical significance, because when they coincide in y values, it is a sign of less difference. We don't want them to coincide in y values, but if the uncertainties are too large, they inevitably will. Now, using the uncertainties formulas, so sum of uncertainties, for example, if you split a 100 meter sprint into two measures every 50 meters, and you have these two times, so the total times is going to be adding the times, and then the uncertainties also add as well. So 0.1 plus 0.2, 0.3. Relative uncertainties when you encounter multiplications of divisions. For example, cardiac output equals stroke volume times heart rate in cardiovascular drift. So first you're going to do the relative uncertainty for stroke volume and heart rate. You have the values here. So here it's going to be the absolute over the value. 2 over 70 gives you this, which would in percentage uncertainty be 0.286%, and here this would be 6.67% for stroke volume. So do both of them, and then you add them up and multiply them by the final value, and it gives you the final uncertainty. So yeah, okay, and the final answer is going to be this. Okay, another example of relative uncertainty, but this time for division, VO2 max. You don't need to know the formula for it. Okay, I have to do the relative uncertainty for all of them if they have an uncertainty. If mass didn't have an uncertainty, then I would just ignore it. So I do it for mass. It gives me this. To find the percentage uncertainty, you would just multiply it by 100. So do it for all of them, and I find that cardiac output here has the highest percentage uncertainty, so it probably suggests it has limited precision compared to the other variables that are measured. Now, the final value without uncertainties is 11.25 when I substitute into the formula the values that I have. And to find the final uncertainty, again, you add them up and multiply them by this final value to give you 1.98. And 1.98 would be added to the final value for this final answer. Last one, amplifying uncertainties. So this is when there's a power involved. It could be squared or cubed. So mass over height squared. Mass, again, I do the relative uncertainty for both of them. And then I do the final answer for BMI. 70 over 1.75 squared equals 22.85. This is the final answer. And by the way, the variable that has the square, so for example height, if I want to do its relative uncertainty, I'm not going to use the square. So here it's mass over height squared, but you have to ignore the height squared for the relative uncertainty. So we know that height is 1.75 plus minus 0.01. Absolute uncertainty over the value without the squared. If it was cubed, without the cubed. And then again, another difference is that it gives me this minus 0.0571, and because I've ignored the squared before, now I need to multiply it by the squared. So multiplied by 2, 0.00571 times 2 plus the other relative uncertainty times the final value gives you this. Now, when the variables are squared or cubed, small measurement errors become more significant. Because as you can see, because we multiplied by 2 here, the uncertainty is going to be larger at the end. Okay. Very important. When you see graphs, you need to identify whether more of the y variable is good or bad in terms of performance. So in this case, because it's the time running a marathon, less time means better performance. You need to identify that straight away. But if it was plank position time, we know that more time doing the plank would mean better performance. And this could be other variables that are not time, but you need to clarify this before you even answer the question. So discuss, so arguments for and against, the hypotheses that the introduction of the CFP shows improvements in caused improvements in running performance post 2016. So supporting the hypothesis, there is no large improvement in performances from 2011 to 2016 here. It just fluctuates. Not supporting the hypothesis, there is insufficient data. There's only one athlete per year. It may not be statistically significant, and there's confounding variables such as the athlete running that day, the environment, the time of the race. Now evaluate the suitability of the line of best fit drawn here. Evaluate arguments for and against. So why it's suitable? It shows a weak correlation post 2016. So you can see a weak correlation here. So it could work, but you should draw two separate lines of best fit here, because here you would draw one here and one post 2016. That would be better. Correlation coefficient. Okay, apart from the obvious that you already know, you may be given a critical value. This is what it says on the syllabus. So if you're getting, for example, 0.69 as a critical value, if the R value is larger than 0.69, okay, if it's then there's statistical significance. This also means that if the R value is negative and it's larger than minus 0.69, there's also statistical significance. Coefficient of determination. So to evaluate a line of best fit with it, if you're given it, or otherwise you can just square the coefficient, the correlation coefficient. The closer it is to 1, because it's always going to be positive, because you know negative times negative still positive. The closer it is to 1, the more suitable the line of best fit is, and the more variation in the y variable is explained by the regression line, which is the same as the line of best fit. So more variation is explained by the line of best fit. If for example, r squared equals 0.1, that's bad, and it means that the line of best fit describes the data poorly. Interpret the data in relation to the shoes. A better running economy means less oxygen is used for the same speed, which means more efficient running. Mean VO2 max is directly proportional to the rate of energy consumption due to aerobic respiration. So more VO2 means you're using more energy. And for example, at 15 kilometers per hour, this is shown, as the moving at higher speeds requires more energy and hence leads to higher mean VO2 max. So the mean VO2 max is higher at 15 than at 14 because they're directly proportional. Now, the lower mean VO2 max shown by the CFP at 15 and 14 suggests a better running economy. Okay, in this case, less VO2 max shows a better running economy because it's not VO2 max, it's the how much oxygen is being used. So not VO2 max, it's just VO2. So if less oxygen is being used with the CFP, as you can see here, it means it causes a better running economy. Now, the high standard deviation indicates lower reliability and hence less statistical significance of the data. And you can see that the standard deviation is larger than the difference between the values. So yeah, it's a large standard deviation. Interpolation and extrapolation, you know from maths. So estimating within the range of data, more reliable, and estimating outside, less reliable. Don't let this catch you off guard. This is a y equals x line, not a line of best fit. You need to differentiate between them. As you can see, 130, 130, 150, 150, 170, 170, it's obviously a line of best fit, a y equals x line. Now, if it was like here, but the values still matched, it would also be a y equals x line. So as long as the y equals the x, and you could see it on the points, y equals x line. Now, this is the time of running marathon cortisol maxing. So less time means better performance. Again, if it was VO2 max, then more VO2 max is better. If it was VO2 oxygen consumption, less oxygen consumption is better because it's just better running economy. Now, Uh, Hence, below y equals x line, points below it means more x value. So in this case, more time wearing traditional shoes, which means that they're slower with traditional shoes than with CFP shoes, meaning CFP shoes are better. But if, again, also depends on the variable. Sometimes being below means worse performance. Now, or better performance. More time with traditional shoes and less with CFP. Yeah. Above the y equals x line means more y value, more time with CFP, meaning worse performance with CFP. If, for example, this was a graph of uh, the weight you can lift pre-training and the weight you can lift if uh, the x values, if the values were below y equals x, that means that you lift more weight pre-training, and if you have more values above y equals x, it means you can lift more weight. So this would mean the training may be stronger. This would mean maybe if it was on the line, there would be no difference. It would depend on the value. Now analyze the data. Athletes with gastric column. So athletes above the diagonal line are slower when they're deep. First, athletes below are faster than and if you Okay. Evaluate the use of a scatter graph and line of best fit to represent this data. Remember that this is running, so less time is better performance. If it was heart rate, then less heart rate would be better. If it was VO2 max, then more would be better. If it was VO2, less would be better, as we saw from the previous example. Now, how would you use how would be appropriate to use the scatter graph line of best fit? So you can have a separate line of best fit for males and females. You could plot a scatter graph of pre-post altitude training with a y equals x line, where the points that lie on the diagonal line or very close to it show no change in performance after the training, uh, meaning the training was useless, but it wasn't bad. Points above the line show more time with post altitude training, if post altitude is going to be the y value, which it will, and more pre, meaning worsening performance, because if there's more time post and less time pre, it means we got worse. And points below the line post and more time pre mean the opposite, performance has improved. Why it's not appropriate? There's insufficient data for a scatter graph, you need more points, and it's an experiment with a manipulated independent variable looking at cause effect, not a correlational study where the scatter graphs are present. Okay, so pilot methodology, small preliminary study before the full-scale project done to test time, cost, risk, and issues. How to reduce bias in study design. Choose representative random samples. Single blinding, double blinding, placebo effect. Randomized allocation of participants to conditions. Crossover study design. So the same athletes receiving different treatments at a specific point in time and specific order. So it's not the same as repeated measures design. It's similar but not the same. And the calibration of measuring apparatus. So for example, if you're looking at a gas syringe and it's new and you want to calibrate it, you, for example, fill it with a certain gas where you already know the density of the gas and set the gas syringe calibrated based on that. A bias is a systematic error, whereas standard deviation or uncertainties are random errors. This is going to be important later. Now, we know how to reduce bias in study design. Now, it may be specific and may ask, suggest two ways to reduce athlete bias, not researcher bias. In the exam, it's probably going to be researcher bias because they use athlete bias this time. But for athlete bias, you can use blinding, or double blinding. And you would explain in context of the question. Now, explain the weaknesses of a study designed based on one athlete. There's insufficient data for conclusions to be drawn. Findings cannot be generalized to the larger population, and the variations in mental and physical factors have a larger impact on performance. The inclusion or exclusion of outliers depends on the following. If it's a measurement error, then exclusion. For example, it's a random error, or especially a systematic error like bias, and you know it is, exclude it. If it's a very large random error, like a very large uncertainty, exclude it. If it's real variation, inclusion, and if you're not sure, you assume it's variation and you include it. Now, what are the strengths of field sports science experiments? It simulates real sports natural conditions and environment, um, and there's less cost of maintenance. However, you can't manipulate or control variables or collect as much data. Now, this is the opposite question, which was in the specimen paper. So, evaluate, so strengths and weaknesses, the use of underwater tanks in sports science. So, strengths, you can manipulate variables and control them. You can collect more data. However, it is difficult to replicate in natural conditions. And there's the building maintenance cost.